Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS in Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will focus on cutting-edge remediation technology to improve site performance. With that, I'd like to introduce our presenters for today. We are pleased to have with us Matt Burns, Technical Fellow and the U.S. Contaminated Land National Service Line Director at WSP. Matt has more than 25 years of professional chemistry and engineering experience. He's based in Boston and is responsible for the financial and technical depth and breadth of the Contaminated Land Site Investigation and Remediation Service Line. Matt also brings chemical and microbial process expertise to assist WSP teams with challenging investigation and remediation projects in the U.S. and across the globe. His area of expertise includes practical application of microbial and chemistry-based innovative remediation. We are also pleased to have with us today Maureen Dooley, Director of Strategic Projects at REGENESIS. Maureen has more than 25 years of experience in the remediation industry. In her current role at REGENESIS, she provides technical leadership for complex soil and groundwater remediation projects throughout North America, as well as remediation design, strategy, and business development in the northeastern United States and eastern Canada. All right, that concludes our introduction, so now I'll hand things over to Maureen to get us started.
Great, thank you, Dane. Welcome, everyone, and I understand how busy people are, so I appreciate you choosing to participate in the webinar presentation today. And the title of today's presentation is Use of Molecular Biological Tools to Define Technical and Economic Efficacy. So we're really pleased to have Matt Burns with us today to make this presentation. And I have the pleasure of working with Matt for many years. And he has an academic level of understanding of complex aspects of remediation, yet he applies this knowledge in a really practical way that results in an effective application of technologies that achieves the goal of obtaining reduced costs to closure. Now, to highlight what Matt's going to be covering today, he will be presenting case studies that demonstrate approaches that can be used to provide more certainty in design and the corresponding results from these applications. I do want to spend a few minutes, however, just discussing some approaches to site design with some thoughts on how we can create some efficiency and describe some of the advanced reagents used in the case study. In this initial slide, when considering in-situ remediation, these 4 tabs on the figure really represent the cornerstones of remediation. And when developing a design, it's really important to consider each of these, with reactivity being related to biological or chemical reactions, such as the ones that are being, considered in, what's effective for your contaminants of concern. In distribution, that's probably one of the most critical aspects of a successful remediation, and our ability to distribute the reagents and get in contact with contaminants. I mean, we speak about contact, but honestly, it's something that is really so critical to the success of any project. Another component is persistence. And I think this is important and sometimes doesn't get enough attention. How long will your reagents persist? Will they be long enough for the desired reaction to go to completion? And so something is an aspect of back diffusion. Is that being taken into consideration? So the persistence associated with some of your reagents is really critical. But finally, the ease of use is also important because we'd like to have our applications as uncomplicated as possible. And as us as practitioners are building our conceptual site model, obviously we take into consideration our contaminant type and distribution, biochemistry, site geology and hydrogeology. And we have now, looking at all of those pieces, a lot of options when it comes to classes of in situ reagents. It can be ISCO, bio, aerobic, anaerobic, sorption, chemical reduction. So we have a lot of options. But what's really going to drive us, I think, when we start focusing in on the application and reagents that might be required for our particular application, it's going to be our treatment time. How quickly do we need to achieve these goals? Is it something that, you're going to be on site for a while, or is this a real estate sort of interaction that where you need to meet these objectives quite quickly? And also, what is our objective? Do we need to get to some low GW1 drinking water type standard? I think the old adage has been that, trying to achieve 99% reduction takes a certain cost, but most of your costs can really be associated with getting to 99.5 or 99.9% reduction. So understanding those targets is really critical. And really what we want to try to focus on today is getting into some efficiencies. How can we increase efficiency and ultimately cut some costs? So molecular biological tools is something that Matt's going to focus on in his presentation. We also can look at design verification or application verification. We've had many different presentations on this topic, and I won't get into a lot of detail on this today, but remember, when you're doing your initial investigation, quite often that's for trying to understand, where the plume is as part of a site investigation, not a remedial application. So collecting additional information, cores, high resolution methodology like MIPS or flux testing can be really critical. But the last thing I want to point out, and something I'll just take a few minutes on, is some of the advanced additives. That now it may be possible to really achieve some of these low targets in PPB or even PPT for some of the case of emerging contaminants. And taking into consideration the application of some of these advanced additives may create some efficiencies and help with cost cutting as well. So I want to just present a couple of the additives that will be used discussed in the presentation today. The first being Plume Stop. Now, Plume Stop is a sorbent, or it's also referred to as liquid activated carbon, and this is designed to remove contamination from groundwater and also promote degradation of groundwater contaminants. The Plume Stop itself is composed of fine particles in the 1 to 2 micron size of activated carbon, and it's suspended in water through the use of a unique polymer dispersion chemistry. Now, the Plume Stop behaves like a colloid, and so it will be, once injected, it will be distributed and then eventually bind to the aquifer matrix. And at that point, you can rapidly sorb contaminants, and then you're going to expedite contaminant degradation. So in essence, what we're doing with the Plume Stop is we're painting the subsurface with this thin film of activated carbon. Now, it can be used for a wide range of sites to help to achieve, a rapid compliance. Maybe you're using it as a cutoff barrier if you're concerned about trying to protect a receptor or offsite migration. It also can be used with other combined technologies. Maybe you've used some other technologies to get to a certain point, you've reached an asymptote, and you're trying to achieve that final low concentration. And this is something where Plume Stop can be quite effective and helpful in trying to achieve these low targets. I think one of the key attributes to the Plume Stop is the ability to manage back diffusion. We're often challenged to have to achieve some of these low cleanup standards, and one of the reasons is back diffusion or matrix diffusion. While we can apply reagents into the high flux permeable zones, as shown in some of the darker areas where you have a more high permeable zone. You inject a reagent, it's going to follow that. But once the reagents are exhausted, the contamination that's bound up in finer grain material is typically going to move into your higher flux zones or your more permeable zones. And so that can often result in this rebound. So when the plume stop, when that's applied, that's going to follow the same flow paths and go into some of the higher flux zones, but it's also going to coat the interface into the interface with the higher flux zones and maybe more coarse material with the finer grain material, and that allows us to manage the back diffusion. And so that the end result is we're able to sustain low target concentrations and have that, extended for a long period of time. The plume stop is also a platform that's designed to support a wide range of biologies and chemistries. So quite often reagents may be applied together or co-applied with the plume stop. So another reagent that is also used quite often with the plume stop is the sulfidated micro ZVI or zero-valent iron. So the sulfidated micro ZVI is a colloidal reagent that's also in the 1 to 4 micron size. But why is this sulfidation? People are talking about this. Why is this really important? Now, the equations that are shown on this figure show the direct reduction of zero-valent iron with PCE. And so we also show the reaction that has zero-valent iron with water. Now, since we're typically in groundwater dealing with an aqueous solution, when the iron is in contact with water, you're going to create this hydrogen. But it's also a bit of a wasted reaction. While you're creating the hydrogen and they may help support biological degradation, if you're not having as efficient an application to the TCE. So what's been found is that if you're able to treat the iron with a coating of iron sulfide, then you're able to increase the efficiency of the zero-valent iron and its reaction with compounds like TCE. So we're maximizing the reactivity with a TCE. And what this figure shows on the side is some work that was conducted looking at where the electrons were actually being affected. And with the bare ZVI, you had most of it with just water, but once you had the sulfidation process, you can see there was a significant increase in efficiency with reactions with TCE. And what we found with some of our internal testing is that if we compare the sulfidated ZVI and the kinetics with just the bare ZVI, we can have a 30-fold increase in reaction kinetics and TCE degradation. And we're also going to significantly minimize the production of any daughter products and a much higher conversion of ethene in ethane. So this is another way where you can create some efficiencies in your reactions using some of these advanced reagents. And also, this is the sulfidated micro ZVI is also colloidal. It's in the 1 to 4 micron size, so it has the small particles. And you can see in the figures shown and the pictures shown on this slide that the colloidal suspension mixes quite easily. And in the tank to the right, these are some sand tank tests that were conducted, and that you can have a very homogeneous transfer of the material through the soil matrix because of the size and the formulation of the sulfidated ZVI. When you look at the comparison with microscale commodity ZVI, you can see that that's a slurry, and really the only way to apply that is under pressure and fractures. So ultimately what happens is you aren't going to have the contact that you would have with the other formulation. So really in closing, in looking at some of the advanced reagents that are available, you can look at things like plume stop and the sulfidated micro ZVI, and you can use these in combination. So the contaminant is going to soar quite quickly to the plume stop particle. You have reactions associated with the abiotic ZVI, and then you can also co-apply with other electron donors and have the also supporting biological degradation taking place. And so while that occurs, the reactions that support the degradation continue to have sorption sites available for additional contaminant. And so this is really the reason when you have the combined plume stop ZVI or electron donors, they're applied together, and you can create this robust and effective combination that really results in the rapid and sustained contaminant reductions that we're looking for. So anyway, with that, that's just an introduction, but now I'd like to turn this over to Matt Burns and start with his part of the presentation.
Thank you, Maureen. We had to do a little bit of a headset transfer there. We had technical difficulties, but we overcame them. So thank you, Maureen, and thank you all of you for attending the webinar. If you find that you'd like to contact us, our email addresses are listed right here on this sheet. You can also get a hold of us through LinkedIn. The registration for this webinar looks very familiar, a lot of familiar names on it. I recognize you, and I've worked with some of you. I see you at conferences. I've read your articles, been to your talks. We run in the same circle. It's really a molecular biological fellowship circle of people. So it's nice to talk with the group again. Thank you for coming back. I keep coming to these fellowship meetings looking for tips that I can take back to my sites, and I'm guessing most of you are here for the same reason. We're searching for knowledge on how to help our clients. And this is why. I think we all realize that in-situ remediation has gotten very complicated. We now know details about degradation pathways that were locked up in black boxes only a few years ago. And there's a lot of degradation pathways that we have knowledge about now. This screenshot alone shows many discrete degradation pathways for chlorinated solvents and petroleum compounds. There's oxidative pathways like direct chemical oxidation, aerobic biooxidation, anaerobic biooxidation, co-metabolic, and even reductive pathways on this sheet that show chemical reduction, hydrogenolysis, elimination pathways. And this is just the first part of the first page of a simple Google search for a contaminant degradation pathway. Further, there are new pathways being identified constantly. I think of these degradation pathways the same as taking a trip in an unfamiliar area before GPS. After every turn I'd take on a road, I'd look for visual clues like landscape features, signs and other signs, try to indicate what road I'm on. Am I on the right place? Observing these clues would let me know they're tests, let me know that I'm on the right path, I'm on the right road, and I'm going to get to my destination if I keep on observing these cues. If I look for these signs at key points, then the consequences of making a wrong turn would never be that significant. If I did not look for these signs very often, then I could end up way off course and maybe not reach my destination. The degradation pathway, or pathways in the case of combined remedies, is the remediation roadmap. The specific reactants and products and number of reactants and products in the equation, of course, vary by contaminant being treated and the pathway being stimulated. Key reactants and products, anything needed to facilitate the reaction, are great candidates to include inside performance monitoring plans. The performance monitoring plans for these type of stimulated treatments don't need to mirror natural attenuation investigations. For natural attenuation investigations, degradation pathways are unknown and need to be identified. And the stoichiometry of the equation, the presence of reactants, the proper conditions to drive the reaction to completion, all need to be figured out. At bioremediation sites, the design engineer selects the pathway to be stimulated and provides proper conditions. Give careful consideration to the amount of reactants, micronutrients you're added, the electron acceptors, the electron donors. They're all needed to drive the reaction or planned out in advance. So performance monitoring is design verification at a working level. It's are there any issues with what I want to do that need to be fixed level? So observing expected trends is evidence of activity along the targeted degradation pathway and realizing our design goals. For me, using molecular biological tools is a knowledgeable way to mitigate risk. This flow chart shows the steps of managing any project or any problem, from grocery store shopping to complex remediation sites. After initiation, all projects go through a planning stage, a performance stage, and a testing stage. If the test is passed, then the project closes. But if the test fails, then you basically need to start over. If you get the pathways wrong, this can become an endless cycle, characterized by a seemingly never-ending routine of quarterly sampling. The way to break the cycle is to insert some actionable data early on in the process. Using the roadmap analogy, look at the landscape. For degradation pathways, natural or stimulated, use some MBTs to make sure the pathway you're trying to manipulate is complete. If the problem is identified early, you'll be able to fix it quickly and minimize your trips around the project management cycle and close the project quickly and permanently. Another way to manage risk is to use the cost and performance equation. Keep costs commensurate with performance. This method uses a black box, but it's understandable. The pathways and MBT black box is a tough one to sort through. We all keep things tucked away in this black box to some extent. And it wasn't all that long ago, before MBTs, that this method of management was really the only option available. So I can understand, I can see how outside of our fellowship, that go to these webinars and read these papers and see you at conferences, new pathways and new diagnostics can seem like a little bit of a science project when proposed at a site. After all, MBTs are not concentration data like cleanup criteria. MBTs are not additional amendment. More is better, right? And it's not easily placed in the performance side of the scale. So for this presentation, rather than strictly feed the fellowship with new pathway diagnostics and new pathways, I'm going to present some case studies that focus on cost and performance. The goal is to demonstrate with a couple case studies how prudent use of molecular biological tools can quantifiably lower costs and improve performance. Here's the outline for the balance of the webinar. We've already completed the blue folder, pathways and actionable data explanation. The two case studies will include one for natural attenuation site and another one at an activated carbon amended site. And we also added ZVI at that site. The first case study is from the central part of the US. This is the natural attenuation site. It's a recently investigated site. Only a couple rounds of sampling data have been collected. It's a large dilute plume with a maximum TCE concentration of about 100 ppb. It's in an oxic sandy aquifer, and no chlorinated sequential reduction data products are present. It's only TCE, no DCE, no vinyl chloride, no ethane, no ethene. There is a receptor, agricultural production wells, that need to be protected. You can see those down at the bottom of the slide. So there is approximately 500,000 cubic meters of affected groundwater that need to be addressed. We took a look initially at using ISCO with permanganate and went so far as to run a bench test. It turned out to be a very low demand site, and we expected that with the sands. But it was still going to cost a fortune to implement just because of the large volume of affected groundwater. But what really ended us considering this as an alternative is that quite a bit of hexavalent chrome was mobilized during the bench test. So based purely on plume distribution, we also noted that there appears to be some attenuation going on, but there's no data products. So if it's occurring, the degradation isn't along the hydrogenolysis sequential reduction pathway. It's got to be something else. Abiotic degradation by an oxy-tolerant ferrous mineral, such as magnetite, or co-metabolism could account for this sort of a trend. So, yep, I think I skipped a little here. I'll go forward. So one of the ways to assess what the pathway is, if you don't know and what a rate might be, is to look at a model. So you plug in your site data into a model and you back your way into a rate. But we have very limited concentration data here, so we wouldn't be able to calibrate a model. And the appropriateness of using literature rates for non-sequential reduction would be highly questionable. There's very few things in literature as far as getting rates with this pathway. So we turn to molecular biological tool, one that I found out about at a conference a couple of years ago, based on work out of Dr. David Friedman's lab at Clemson. And it's also based on some diagnostics offered by Microbial Insights. Dr. Friedman has developed a C14 assay, so that's not C12, the 99% abundance, is not the C13 with the 1% abundance. This is the C14, the radioactive version, that's very less than 1%, much less than 1% abundance. So Dr. Friedman has developed a C14 assay to quantify the rate of TCE degradation along abiotic and co-metabolic pathways. If you like details on this diagnostic, you can find a webinar by Dr. Friedman on the Microbial Insights website. This slide provides some detail on the suite of analysis used to assess the abiotic pathway. In addition to the C14 assay, Microbial Insights estimated the amount of iron minerals present by magnetic susceptibility analysis. This data is comparable to data from other sites where relationships between magnetic susceptibility and the rate of TCE degradation has already been determined. For the co-metabolic assessment, the C14 assays were used in the presence of co-metabolic oxygenase genes were also assessed. Well, here are the results. TCE degradation was quantified in one of the 4 samples that we submitted for analysis in both the co-metabolic and abiotic assays. So we had 1 hit in the co-metabolic and 1 rate determined in the abiotic. It's not great, but it's better than not having any rates determined in any of the samples. And if we squint a little bit and maybe divide by 4, we can come up with a rate of 0.04 per year. Without squinting, at the bottom of the page, you can see the magnetic susceptibility data. That was very consistent across all the samples at about 2e to the -7 meters cubed per kilogram. So let's take a look and see what that means. The magnetic susceptibility results that we've obtained at the site compared to literature values. This is data from the BioPIC document. You can download the BioPIC document from the CERTIP ESTPC website if you like. It's a great document and I encourage everyone to take a look at it. You can see the site data plot similarly to the data from Hopewell. I'm really glad they included Hopewell in this study. It could have easily been out in the cold as a comparison to this site. The degradation at Hopewell was around 0.06 per year, which is very close to the 0.04 per year we got by squinting in the previous slide with the C14 assays. So we plugged the data into a site model. We used REMchlor and plugged that 0.06 per year degradation rate into REMchlor along with all sorts of other characteristics that we collected just to be able to make sure we could build a robust model. And we had no issues with the calibration. We, in predictive simulations, showed that the plume would not get beyond the already impacted property at a concentration greater than our standard of 5 micrograms per liter. This is just within the goal of just within our goal of not going beyond the property that had some use restrictions on it. So the next steps at this site involve a couple of years of quarterly monitoring to further validate the model. And if the model is validated, we'll get regulatory closure. Now for the cost and performance assessment of this this site. So there are 500,000 meters of affected groundwater. You take that volume and multiply it by any cost per cubic meter, it comes out to a huge number. So you can pick your own number in there, but it's going to be a big number to treat this entire plume using a conventional method. On the other hand, the diagnostics cost $10,621.57. That's inclusive of the microbial insights work and the work by Dr. Friedman. The entire cost of closure, if the model is validated, adds up to about $200,000. So I think you can see the cost benefit of doing the molecular biological tools, or using the C14 assays and the other tools to validate the natural attenuation was occurring at this site. Case study 2 is a sorbent treated site. It's located in Canada. It's actually the first application of plume stop and the sterically stabilized sulfonated ZVI product that Maureen talked to us about. The site's located in northern Quebec, and I was fortunate to work on this project with my colleague and friend Luc Turbide from our Montreal office. This case study is also subject of a pamphlet that you can download from the REGENESIS website. The site's a rail yard that historically used chlorinated solvents. Operations led to discrete releases of petroleum and chlorinated solvents. I'll be focusing on groundwater with chlorinated ethanes and ethenes, and the reductive abiotic products are the primary concern. It is a primary concern because of the presence of down-gradient residential wells. See if I can point to them. Well, I can't, the pointer's not working on this, but it's at the very bottom of that map. You can see residential wells identified. So if a plume's not all that far from it. The green outline indicates concentrations of chlorinated VOCs that were measured that between the drinking water standard and non-detect, and above the drinking water standard is outlined in red. The site had been investigated for years, and there's not enough time to go through that, but one of the key pieces of information about the site was derived from a MIP investigation. Specifically, key findings in the MIP investigation survey identified the bulk of the VOC mass is limited to narrow interbedded transmissive zones within a heterogeneous silt and sandy aquifer. And the plume was relatively narrow. So this is where we decided to conduct a pilot test, the same area where we investigated with the MIP. Here I zoomed into the pilot test area to show the injection and monitoring well layout. You can see the red MIP points, the green direct push pilot injection points, and the 4 monitoring wells that were installed to assess performance of the pilot. The 2 points in the treatment zone and 1 point, 2 wells were within the treatment zone, and 1 up gradient and 1 down gradient. That's where we collected our analytical data and performance monitoring data. These wells were installed a few weeks or about a month before the injections occurred. Here's an injection, a photo of the injection layout. I mentioned in the intro slide that we applied plume stop and the sulfonated ZVI at this site. We also applied a bioaugment and a fermentable donor. We felt comfortable with this combined remedy, the formulation of this combined remedy, because activated carbon is an established technology. After decades of use ex situ, we know about how it behaves in the presence of VOCs. Also, earlier investigations provided info about bioremediation feasibility. Here's a quick look at some of the earlier molecular biological tool data we collected that was responsible for our confidence in this combined remedy. First we noted that there appears to be some natural attenuation based on VOC distribution. Isotopic data confirmed that there is natural attenuation going on. We saw enrichment along the flow path. But there was minimal accumulation of vinyl chloride or ethane and ethene, despite having enriched vinyl chloride and DCE. So complete degradation isn't solely attributable to sequential reduction or hydrogenolysis, or there'd be a lot more ethene present. Mineralogical data showing the presence of reduced iron minerals known to degrade along the abiotic pathways are consistent with apparent natural degradation and the lack of hydrogenolysis. As we discussed in the previous slide, the abiotic pathway doesn't produce as much daughter product mass or ethane, ethene, and that could be one of the explanations for why we're seeing natural attenuation. We also did baited in situ microcosm studies using biotraps, and those also demonstrated degradation, the ability to stimulate complete degradation along the hydrogenolysis pathway. All right, so let's move on to what we did around the injections. So immediately before the injections, not immediately, about a week or two before the injections, we deployed in situ microcosms to each of the monitoring wells. So the monitoring wells would be the 2 wells that were within the plume and the 2 wells that were one up gradient and one down gradient of the application area. Here's some photos of the ISMs. The ISMs were constructed by taking natural aquifer material that had been dried out, and we placed them into a 1-inch diameter well screen. And then we deployed several of these into each well so that they could be collected discreetly following treatment. Again, these native aquifer material ISMs were deployed a few days, about a week or so before amendment injections were made. The goal of the ISM samplers was to quantify degradation on the plume stop particle. This is needed because sorption will limit our ability to assess degradation from aqueous samples alone, from the groundwater alone. The higher molecular weight compounds will partition into the activated carbon, or they should. We just put activated carbon in there. So moving on to the implementation, here's the amendment application statistics. Overall, the application went very well for a wintry November. Minimal applied pressure was needed, although we did see some back pressure following the injections, not very much though. We also saw some immediate indications of distribution of the amendment with geochemical shifts and visual cues within the 2 monitoring wells located within the barrier. The footprint of the amendment distribution and expected geochemical changes in response to the amendment are shown here. The heat map shows rounds of observation, one during injection, which includes visual and field parameter observations, and one about 10 months later that include more comprehensive list of parameters. The green shows changes consistent with delivery, like the water turned black. Black's the same color as the plume stop. Yellow showed moderate changes, and red really nothing at all. All of this was as compared to baseline conditions from before the amendment application. For example, the top row is a visual cue observation of the amendment. So it's green within the application area, in yellow and to red in the up gradient and down gradient, indicating very little presence of delivery in the up gradient or evidence of delivery in the up gradient or down gradient wells, but lots of evidence of great delivery within the application area. This slide shows groundwater VOC data and mole fraction data. The x-axis of each plot shows dates and of the baseline and performance monitoring sample. The y-axis shows the total VOC concentrations in milligrams per liter. The mole fraction is shown in the pie chart that plots the total VOC concentrations. Red is equal to TCE, and TCA, yellow DCE and DCA, green vinyl chloride. You can see that the samples collected from within the barrier, PO2 and PO3, show significant groundwater concentration decreases with treatment. Exactly what you would hope for and even expect with activated carbon treatment, as we mentioned a couple slides ago. By contrast, not as much has changed in the samples collected from PO1 and PO4, the up gradient and down gradient wells, where we did not see much evidence of delivery. This slide shows the SORB VOC data and mole fraction information collected from the ISMs. So those ISMs we deployed before treatment, we pulled one of those out and sent it off for soil analysis. And this is the data. The graph and pie chart have the same setup as the aqueous phase data plots. The plots from PO2 and PO3 showed data, no or next to no SORB VOC mass. This is after treatment. So no VOCs in the groundwater, none in the SORB to the plume stop. That's a great mass balance. That mass balance demonstrates that we just didn't get partitioning here. We got contaminant destruction. We also collected some advanced diagnostic data. Here are some plots of CSIA data collected from the groundwater. CSIA data provides definitive evidence of contaminant destruction. In this plot, the total VOCs are shown in black, and the parent and daughter CSIA VOCs plotted on lines that use the same color scheme as the previous slides. Note that in both PO2 and PO3, the slopes of vinyl chloride, and in DCE and PO2 are positive. This indicates fractionation, or definitive evidence of complete treatment. The extent fractionation here provides, again, definitive evidence that destruction has occurred and is entirely consistent with both the aqueous and SORB phase concentration data shown on the previous slides. In conclusion, we applied plume stop and the sulfonated ZVI. It was, first application of this, this combination globally, and we got great amendment distribution. I've done a bunch of these since then, and that seems to be the rule, not the exception. I expect great distribution with these amendments. We got great destruction with the SORB phase and definitive confirmation of destruction with CSIA. In short, the pilot test was completely successful in demonstrating site-specific applicability of the technology. So the next steps here is consider expanding the application to take it a little bit beyond. This is a large pilot test, but let's finish the line. And certainly reduce the analytical suite, as the molecular biological tools have already provided the definitive information that's needed about site-specific efficacy. And here are the MBT costs, about $30,000. This slide shows the projected 10-year costs for the in-situ remediation. So if we run this for 10 years, the green bars show in-situ, and this is all compared to a pump and treat alternative that this in-situ option has replaced. Those are shown in the blue bars. Supporting math is in the table below. So not only were capital costs of the pump and treat higher than the in-situ remedy, but other than monitoring, the O&M costs for the in-situ option were limited to periodic application of the fermentable electron donor and to stimulate the biodegradation. Because the donor will run out after time, we'll have to reapply. In total, the molecular biological tools, these molecular biological tools in this application have led to about $1 million in savings, or projected savings, and these are discounted over a 10-year period. So in conclusion, thoughtful consideration of degradation pathways and a little bit of MBT use tips the cost and performance scale in favor of in a favorable and quantifiable manner. Further, I want to stress that molecular biological tool data collection, and really all data collection, should be limited to actionable use. It should answer a specific question. Once the question is answered, there's no need to make it routine. There's no need to spend tons of money all the time quarterly. Prove a point and be done with it. Collecting data without purpose is unnecessary and tilts the cost and performance equation in the wrong direction. And with that, I think we can open it up to questions.
All right. Thank you, Matt. Yeah, that does conclude the formal section of our presentation. So at this point, we were ready to shift into the question and answer portion of the webcast. Before we do that, just a couple of quick reminders. First, you will receive a follow-up email with a brief survey. We really appreciate your feedback, so please take a minute to let us know how we did. Also, after the webinar, you will receive a link to the recording as soon as it is available. All right, so let's circle back to the questions here. Let's see, we have a question here for Maureen. Maureen, the question here is, could you speak to the effectiveness of plume stop in remediating PCP in groundwater, or would you recommend the use of ZVI instead?
Hi, Dane. Yes, so I want to make sure it's PCP, pentachlorophenols, and not PCB, but I may answer it in both ways. I think for any compound like PCP or PCB, those compounds would be, would sorb quite readily. The isotherms would be, oh, it is PCP. Okay, great. Assuming anything that sorbs to the activated carbon, you can consider for plume stop. So looking at something that is, so something for PCP, I think that could be a really ideal amendment to consider. What you're going to look at are some of the concentrations. Now you talk about the application or the use of ZVI. ZVI could be used in combination. I'd probably, look at a combination instead of a one versus the other, ZVI or plume stop. It's my understanding, and I'd have to check with Dr. John Freem, on PCP and, ZVI application, but my understanding is it would be a likely degradation pathway. But for something like PCP, you might want to run some lab tests just to confirm the efficacy of using something like the sulfidated iron, with the PCP. But to answer your question, I think you could consider either, and probably a combination might be ideal of the two products. Yeah, 6,500 parts per billion apparently is the highest concentration. Yeah, I would definitely use a combination, because usually with plume stop, we're probably at that 10 ppm-ish range as an upper
I think you cut out there for a second, Maureen. Are you still with us?
Dane, I'm with you. So for some reason we're getting intermittent cutouts of our headphones, but do you need anything else on the pentachlorophenol?
Okay.
Let's go to the next one, Dane.
All right, sounds good. Let's see here. So the next question, this one is for Maureen. I don't know if Maureen's still able to.
Yep, I'm good.
Okay, great.
I'm back.
All right, great. Okay, so the question is the increased reaction with sulfidated ZVI only limited to chlorinated solvents, or do you see the increased reactions with other contaminants as well?
The data that we have for the use of sulfidated iron with is with primarily with the VOC, so we know that works. And so probably what we would suggest at this point for any other contaminants, it might be a case-by-case basis, and it's something we'd want to look at individually. So let's say most of the data we have are with the chlorinated solvents, and we would just look at case by case, and it's something you could contact us, and we could get you in touch again with Dr. Freeman. He could, probably have some specific comment if it's something outside the VOCs.
All right. Okay. Well, thank you very much, Maureen, and thank you, Matt. That is going to be the end of our chat questions. So if you'd like more information about engineering solutions from WSP, please visit WSP.com. And if you want to learn more about remediation solutions from REGENESIS, please visit regenesis.com. Thanks again to Matt Burns and Maureen Dooley, and thanks to everyone who could join us. Have a great day.